Okay, so welcome everyone, and today we are happy to have a talk by Karapet Mkrtchyan, and he's going to speak about interactions of fermions in 3D. So please go ahead.
Thank you, Timo, and thank you for the invitation to speak here. So I will talk about recent work with Stefan Fredenhagen and Philip Lausch, but I will also summarize the general context and the current state of the art in a more general setup. In Fronsdal program, which is constructing interactions for higher spin theories in a specific metric-like formulation. And the Fang here stands for adding fermions because Fronsdal fields are the bosonic massless higher spin fields, and Fang Fronsdal are the fermionic ones. So I will start from a general description of the general problem, which Fronsdal program is part of an attempt to solve general problem, which is I will try to define even more generally than higher spin problem, and this is mostly something that is familiar to this audience. Then I will go into more details about general construction of higher spin actions. Again, mostly not new stuff, and I will concentrate later on the 3 dimensions, in particular mostly work that is done within the last 5-6 years, but I will end with the most new results, which are the fermionic interactions in 3 dimensions. And I will not really be complete in also giving references. I'm guessing that in this audience, most of you are familiar with most of the developments in the field, but also mostly many of you contributed into this development. So, but I will try to give some references selectively where I remember to include some important key references. So the main problem that we all are interested in is the quantum gravity, and then there are many different approaches to it. I will try to formulate a problem that is kind of, in my opinion, key to this general quest for quantum gravity, and maybe can hold some keys if we define it broadly enough and find a solution to this problem. So the examples of successful framework for quantum gravity are not many, and we know string game theory are these examples, and it's almost unique formulation of quantum gravity, and it necessarily comes with the towers of higher spins, and these massive higher spins are necessarily in some phase maybe considered as massless, or at least there are some limits where one has to deal with massless higher spins, and natural question comes how to deal with theories that contain massless higher spins. And similarly related to string theory, but maybe can be viewed as an independent operational framework, is holography, where one again trying to look at the simplest possible cases where one can treat the quantum gravity again faces the problem that we need massless higher spins, and this necessarily come with their gate symmetries and corresponding global symmetries that are infinite dimensional, and these are normally hard to realize in field theory. So the general lesson that I believe we can take from the successful frameworks of quantum gravity is that in order to have a full description, we have to understand how to treat massless higher spins, which come necessarily with some extended space-time symmetries, which I will define a bit more concretely in the following. So here I will generally mention extended space-time symmetries, which is an example of it is higher spin symmetries, but maybe one can define a bit more generally, is that it's the symmetry that extends the given isometry algebra of the space-time by involving at least one more generator that is in a non-trivial representation of the isometry. And this is usually enough already to have some clash with standard field theory. And as we know from the works of Mandula, Weinberg, so there are very old arguments, mostly S-matrix arguments about incompatibility of such symmetries with non-trivial scattering. But I will try to define the problem a bit more broadly, which is that this is so as far as I know, this is not that much discussed in the literature, but I try to formulate a problem that is generic enough. So this is a list of 5 qualities or properties of a field theory that are hard to combine. It's mostly about classical field theory, even though the motivation comes from quantum theory, but the problem is itself classical. So we want to have extended space-time symmetries, and we can even concentrate only bosonic symmetries. And we want to have local action principle in our theory, unitarity, non-trivial bulk propagation, and non-trivial interactions. Here, by bulk propagation, again, it's a bit hard to formally define. What I mean is that if we have a theory that has a maximal space-time dimension in which it lives, if this is a well-defined concept, then there should be non-trivial propagating degrees of freedom in this maximal space-time dimension. This is somehow crucial in most of the no-go theorems, even though it's not specified. So the interesting observation that I believe can be useful in looking at this theory is that none of these properties are by themselves problematic. The problem is to combine all 5, and one can explicitly show examples with any 4 of these properties. So normally all no-go theorems naturally assume all the properties from 2 to 5, but therefore they prove that the property 1 is problematic, but in general this is not the case because one can remove one of the other properties, and again there are examples of theories. If we remove the first one, it's obvious that given Einstein gravity satisfies all the criteria, but if we remove other properties, there are examples. For example, if we don't need local action principle, then Vasilyev's higher spin gravity is a theory with extended symmetries that has all the properties except for local action. If we exclude unitarity, then there are many possible theories, including conformal gravity as the simplest example, or conformal higher spin gravity, even which has infinite dimensional symmetry. If we exclude non-trivial bulk propagation, then we have higher spin gravities in 3D that are given in terms of Chern-Simons actions and do not have bulk propagation, but describe boundary degrees of freedom. If we exclude the non-trivial interactions, or alternatively, we can exclude the well-defined free limit, then there are also examples. So either free theory or strongly coupled theories that don't have free limit can still overcome these no-go theorems. So what we want is a theory that can be perturbatively constructed from free theory by adding interactions. One may argue that in principle there are examples that have all these 5 properties, but it's this argument is a bit shaky in the sense that in order to prove one of the properties, one has to give up the other property, but implicitly in some way. So, for example, if we define unitarity based on the scattering amplitudes as matrix, then if the trivial S matrix is unitary, then starting from a non-unitary theory, one can get, there are examples where you actually compute S matrix and it's trivial, then that would somehow save unitarity if unitarity is defined as some property of S matrix. This is an example is chiral higher spins, but also in principle conformal higher spins could be an example. We know that this is clearly coming with Ostogradsky costs, but S matrix due to symmetries can be trivial. Another formulation of this general problem that I could find clear formulation is by Edward Witten from Strings Talk in 2017, where he's mentioning that we need some understanding of the quantum classical descriptions of quantum gravity theories that are holographically equal to the simplest boundary conformal systems, like in the case of Vasiliev theory or the dual of the SYK model. And this basically, again, is another way of saying that we need actually understanding of the classical action formulation for candidate theories, and one of the simplest examples is higher spin gravity. So this most standard formulation to higher spin degrees of freedom, massless higher spins, is basically a Fronsdal formulation that dates back from 70s, and the metric-like higher spin formulation. But there is also the frame-like formulation, as probably familiar to everyone here. So the Vasiliev equations are formulated in terms of frame-like equations of motion, but the action is not known. While when trying to construct the action in the Fronsdal variables, then so the study in dimensions 4 and higher indicates that after cubic order, the interactive theory somehow may need a drastic paradigm shift, because the standard field theoretical arguments of constructing order by order local Lagrangian does not seem to work. In 3 dimensions, the situation is slightly different, in the sense that for the examples where there are no propagating degrees of freedom, there are actions, there's Chern-Simons formulation, and so on. And in the matter-coupled case, which is more similar in a sense to higher dimensional case and has propagating degrees of freedom, we still don't have action formulation. On the other hand, with this Chern-Simons formulation, it's hard to couple matter, so one could refer to more standard Fronsdal program in 3 dimensions to construct full actions with matter coupling, and this is the main motivation to do Fronsdal program in 3 dimensions, but also because in 3 dimensions we know how to couple matter to Fronsdal fields. On top of that, we also know that all the other no-go theorems that are normally present for higher spins in 3D are not they are not working, at least directly, they are not working in the same way. And so when we don't have matter coupling, then in principle Fronsdal program can be theoretically completed even for systems with finitely many higher spins, because we know that the Chern-Simons counterpart exists. Therefore, there is no problem of constructing an action. While the matter-coupled theory is the most interesting, already the examples without matter, so far there is no full Lagrangians similar to Einstein gravity in a sense for higher spins, and this is by itself is also interesting because it may teach us some lessons, even though we don't expect too much surprises. So this is the state of the art and why to study 3D Fronsdal program. Now I will review a bit general Fronsdal program. So the Lagrangian for massless higher spins, 3 massless higher spins in arbitrary dimensions are given by the Fronsdal Lagrangian that is described in the first line, and the Fang Fronsdal Lagrangian in the second line. And the terms that are need to be added for the full Lagrangian is the terms that are we are going to omit because they contain divergences and traces, and we will not necessarily need all of them for our purposes, and they are fixed by gate symmetries, and the gate symmetries are given by traceless and gamma traceless parameters. And I will always not denote S the spin of the fields, and whenever they are fermionic, there will be integer part of the denoted by L, just for notational purposes. And an important comment would be that for spin higher than 1, this Lagrangians of Fronsdal do not contain propagating degrees of freedom in the bulk for dimensions 3 and lower. We will be interested only in 3 dimensions in the future. But the Fronsdal program is general. As I mentioned, in arbitrary dimensions, one can do this construction starting from free action. So generically assuming that there is a full nonlinear action that involves some fields that are collectively denoted phi here. And it can be expanded in the powers of the fields where quadratic action is the first term and then the higher order terms. Normally, all possible powers of fields interactions may be included, but when classifying the general interactions, one has to map all possible independent deformations, and they may start not at the cubic but general end order, and that's why we can introduce in this form the general for arbitrary coupling constants that are responsible for interactions that start at the n+2 order, and correspondingly one can derive all possible consequences of gauge invariance, which are given as equations at each order, and this first order is always assumed to be the free theory that is given by Fronsdal action, or Fronsdal in the fermionic case. Now, if we have a lowest order interaction that starts at the n+2 order, then there is an equation of motion which allows to derive general restrictions on possible interactions, and given that the variation of the quadratic action is always proportional to free equations of motion, one can write a weaker equation, which is that the variation of the lowest order of the interactions is always weakly 0, which means that it's proportional to free equations of motion. And this equation is what one needs to solve to find general interactions at arbitrary order, that start at arbitrary order. And the lowest possible order where one can start interactions is cubic, and for some reasons I will mention also later, this is also the most important in this setup when analyzing the interacting theory. And so we basically get the equations for cubic deformations where again this phi's are collective fields, and is in principle one can have many different coupling constants. This is just schematic structure, and then one can solve the equations starting from the second in these lines to derive interaction for higher spins at the cubic order. Now, the gauge algebra generically also is expanded in the number of fields, and one can write it in terms of I didn't write this equation. This delta is the full nonlinear, but one can expand it as 0 order, first order, second order, and 0 order would be the free gauge transformations that do not contain fields, but only the parameters and their derivatives. And the first order of this commutator equation implies that once we have the delta 1, we can derive what is the commutator of gauge parameters. And once we have this the delta 2 also, then we can derive the global symmetry in a sense. So the commutator of first-order gauge transformations, which, as I will mention now, will define the global symmetry of their theory. So the global symmetry will be defined as gauge symmetry with those parameters for which delta 0 phi is 0. So this is the killing parameters. Then if we can omit this part here, then we can clearly say that there's a part of the transformations that close under the bracket that is defined here. So that means we have some subsector of gauge transformations which are given by global parameters that forms the global symmetry algebra. And that is why the cubic interactions are important, because they define delta 1 for which we get from which we can extract the global symmetry algebra. And this is clear from once we solve the cubic action, so we find the most general cubic vertices, then we can plug it back into the full equation. And since we know everything here except for delta 1, this gives us delta 1, which is crucial for the global symmetries. Once we know delta 1, then we can again use this equation, but restricting to global parameters, so killing tensors. Then we get the equation which is saying that the free action is invariant under the global symmetry, which is basically a statement that the particle spectrum of the theory is a representation of the global symmetry algebra. This is, in a sense, nothing new, but in the context of higher spins, this can be a very powerful statement. And it is, in a sense, implicitly explained in an old paper by Konstein and Vasilyev. Maybe I made a typo here, I'm sorry about that. In this language, it is explained in our paper with Ehan, and in the relatively more recent paper, we explore how most of the no-go theorems that we know about higher spins, color gravity, and everything can be understood in this language, in the sense that if you are trying to construct a theory for which the candidate global symmetry algebra a priori cannot have representations that would fit the particle spectrum that you start with, then there is no chance you will get a nonlinear theory, and this is immediately excluding a lot of candidate theories. So even though as a statement it looks like trivial, but somehow it can immediately lead to strong conclusions in this setup. When we already solved the cubic interactions, then we can go to higher orders.
Karapet,
yes?
Sorry, just one question. But it's I remember from old times that Vasilyev was always saying that if you want an deformation of your gauge symmetry, you need your multiplet to be invariant and to multiplet to be representation of the same algebra, but as a global, like high-speed algebra.
Yes, this is exactly the same statement.
But sometimes it is explained more in terms of like gauging of global symmetry, right?
Yes,
if you have a global symmetry, you can couple it to you have it's more traditional maybe point of view. Well, anyway, it's the same story.
The statement is more generic, yes, in a sense that you can have, for example, whether you use metric or frame formulation, you gauge full of the global symmetry or part of it. It doesn't matter that much anyway. Whatever theory you construct, the multiplet has to be representation of the global symmetry. So in a sense, this is a bit more generic than independent on what is the formulation of the or what field variables that you use.
Okay. Yeah.
So,
sorry, can I ask something? Where does this come from? I mean, it is, for example, the fact that global symmetry is close.
So this is just simply following, generically assuming that there is a full nonlinear gauge symmetry, which we might not know yet. We just write this commutator of it and the expanding power of fields, and we can see very quickly. So important thing is that maybe I went too fast in this part. So I cannot find in which slide I was commenting about this. So all of the higher spins. So this is discussion in the context of higher spins, of course. But all of the fields in a Lorentz preserving background have to have a zero VAV, right? So that means that this would be my transformations that do not change the vacuum. So this is the global symmetry. And for that, it is just straightforward from this equation that the commutator of first order transformations are basically closed under those parameters for which delta 0 is 0. So does this answer your question?
Do you know the reference where it was originally?
Original term. So there are many references, but I think so. Here we explain it in detail, and we refer to earlier papers. In particular, I think there was a paper by Xavier and Nicolas about killing tensors. That is older, 2008.
No, but I think it's really classical stuff.
Yes, but I don't remember original.
It contains structure constants of a certain algebra. Constants because it is cubic, and algebra because it is cubic. And if you have killings, these killings form the same algebra. And from the equation you have on, I don't know, but it is, I can't help with, reference, but it seems to be a kind of standard knowledge explained in different places in different formalisms. And then the question in which formalism it is in. It's straightforward in Vasiliev formalism. It's also straightforward in BRST, and there is an explanation more concrete like this. But yeah, okay.
So yeah, to my best memory, I mean, when I need to remind myself details of this, I go to this paper. To my best memory, there's earlier literature that may not have all the details needed for this higher spin setup. So it is not a new knowledge, but we kind of try to spell out in a way that is making it more clear somehow. So, what I wanted to add to this is, so in principle, there can be difference between the gauge and global algebras in this setup because, for example, if we could construct full nonlinear metric like higher spins, then the gauge symmetry generators will be only the Fronsdal gauge parameters, which is much less than the global algebra generators that contain the frame like old generators. But the global symmetry would be, more important in the context of finding what is the spectrum. Spectrum should be representation of the global, not the gauge symmetry. So in this sense, global symmetry is playing in crucial role. But also, so when we try to go to higher orders, actually there is a interesting observation again here that if we are restricting ourselves to killing tensors, then the next equation, which contains quartic interactions, boils down to a condition only on the cubic vertices. So this condition by itself, because we are restricting to killing tensors, so delta 0 is 0, we don't have the quartic contribution, and we are restricting to weak equality on free shell, which also drops the first term. Then this condition is a condition on the cubic coefficients, basically. And if you do this for the Young-Mills, I didn't really do it, but I'm sure this works. So it basically implies, so for the cubic interactions, we construct for Yang-Mills, we get that we need an antisymmetric structure constant, and then this condition would imply the Jacobi identity. So this already by itself restricts very strongly and basically gives almost all the information about the relative couplings for cubic vertices. And indeed, an example of this is constructing the equal for theory in the Lightcon setup. So all the coupling constants get fixed even without any knowledge about the quartic vertex. Even though this is a different formulation and maybe technically it is done differently, but the idea I think is the same. So then the next, in this case, the only example where the theory is complete is the chiral case by Mitya and Genia. But for general theory, in principle, the cubic couplings are still fixed, even though, the quartic coupling, quartic action is not yet understood or might not exist in this setup because it requires some non-locality or something. So this question is still open, but the fact that the cubic couplings get immediately related due to this property of the global symmetry is by itself very useful. And using this, we are now working on the 3D analog of this Fronsdal program by imposing the closure of the global symmetry algebra. We are able to fix coupling constants and so on. Now I will quickly get into more details. This is just maybe familiar to many of you, just using these auxiliary vector fields to compactly write the expressions with many Lorentz indices, and then we can write the operators like divergence, trace, and so on in a very compact way. This allows to also simplify analysis for interactions, and in fact, so if we have a cubic interaction vertex, all of the contractions can be written in terms of these variables that are very convenient. So we can, at the cubic order, we can drop all the contractions of derivatives between themselves because they're proportional to D'Alembertian operators acting on the fields, which on shell we will drop, and also we will be using traceless transverse conditions, so divergences and traces will be dropped. Then things get simplify a lot, and one can write the arbitrary cubic interactions as functions of the 6 variables, which are this y and z, which are contractions of derivatives with some of the fields and contractions of fields between themselves. So this is all one can have with the Fronsdal fields and the Lorentz covariant structures. So then for the bosonic interactions for arbitrary dimensions with Fronsdal fields, this basically boils down into writing operator that is dependent on the 6 variables, and this naturally can be understood as generating function of all possible interactions that involve arbitrary triplets of S1, S2, S3 spins, and there's an extra label of counting number of different cubic vertices, and this can be very simply used to find the conditions imposed by gauge invariance, and the gauge invariance imposes on the vertex generating operator an equation that is first order differential equation, or actually 3 of such equations, which can be simply solved. These equations are not fully independent. That's why we get the solution that has 4, not 3 variables. So this is basically the expression G and Y are gauge invariant combinations that solve this equation. And then for arbitrary S1, S2, S3, we get that there are lists of vertices. And this classification of vertices is known from Metsaev's work in LightCon, and it basically has minimal and maximal number of derivatives. The minimal clearly would be needed because we need derivatives for gauge invariant structures, and the maximal is clear because we cannot have too many derivatives, otherwise they will start to contract each other, and that is on-shell trivial. And so the this classification of vertices in the covariant languages work I did with Mavelian and Rule during my PhD in 2010. And a year later, actually, there was another work constructing the 3-point functions of conserved currents in CFDT-1 and getting exactly the same structures in the sense that it's matching these vertices. Then if one goes beyond cubic order, then situation gets a bit complicated. There are maybe infinitely many statements about no-go theorems, and these are all maybe with some hidden assumptions or quite generic in a sense. So I will not review all of these no-go theorems. I think the most recent review I've seen is this paper by Mkrtchyan. The oldest and strongest argument is actually based on minimal coupling to gravity, which is called also known as Aragon-Tezer problem. But this problem is kind of milder in ADS, and this is the Radkin-Vassiliev solution to the Aragon-Tezer problem. The metric-like analog of this is given by Jung and Tarona in 2015. And this is basically saying that when there is no minimal coupling in flat space, actually in ADS, there is a minimal coupling due to some deformation of the vertices in ADS, and somehow the coupling induces diffeomorphism transformations for higher spins, which naturally leads to what we can call minimal coupling. Going beyond the cubic order is explored mostly in the context that whether we can do some non-local completions and whether what is an accepted non-locality and so on. As the first oldest that I remember is the discussion in these papers. There are also some no-go theorems before and some discussions after. Maybe I'm missing some important references. Maybe more recently, Mitya had some work related to this non-localities. Sorry for missing it. Another interesting avenue to go around these no-go theorems is to add some fields, and an example that was studied is to add a ghost spectrum by Royban and Arkady. And another idea that was also expressed in this work was that maybe there is some non-local conformal completion which could be explored further in principle. So yeah, for the moment, this is a situation of the higher dimensional Fronsdal program, which is in a sense unsatisfactory because we only have a lot of no-go theorems, but we know that there has to be a theory, and we are still proving that it doesn't exist, which is somehow not very useful. I mean, it's useful in the sense of learning something, but eventually we need to go around the no-go theorems. That's the most interesting part. So just a quick reminder of how these vertices look like. It's like I was writing these expressions y, g, and so on. So the simplest one would be the vertex coupling your scalars to Maxwell field. And when we have three spin 1 fields, then there are two possible vertices, which is F cube and Young-Mills. And when we have purely gravitational vertices, there are three. Again, this is a well-known thing. Maybe, again, I could have mentioned some old literature where this was classified. In particular, I think Metsaev had worked on this long before this was common knowledge. So the 3 vertices in the standard language can be understood as Weyl-Cube, Gauss-Bonnet, and Einstein-Hilbert. And we can also notice from here that any purely gravitational vertex is a product of 2 spin-1 vertices, which might be somehow hinting on some connection to double copy, although this part is in a sense a bit trivial. So an interesting observation is that the vertices that are in arbitrary dimension work also in 4 dimensions, but some of them become trivial. So there is a Schotten identity that one can get by antisymmetrizing 5 indices in 4 dimensions that has to be 0, and this says that Gauss-Bonnet vertex is trivial. And naturally, I mean, this is the first instance, but there are much more higher spin vertices that are trivial. And in fact, for arbitrary triplet of higher spins, we are getting that there are at most 2 vertices, and the general vertex will contain such a structure that makes it trivial. So one has to choose extreme cases for this n, so that it's either 0 or the maximal possible number. In that cases, we get 2 different vertices. One is the maximal vertex, which has as many derivatives as the sum of the spins, and the other is the minimal vertex. In 4D, there is also specifics that one can also write paradiode vertices. I will not go into that, but for each of these, there is also paradiode cousin. And then in 4D, what is special is that there are vertices in light cone or in amplitudes that cannot be written in terms of Fronsdal fields, which is very intriguing. Now, what to do in 3 dimensions? So I will go a bit faster maybe, because so in 3 dimensions the situation is completely different, as opposed to 4 dimensions where there some Schotten identities trivialize some vertices, but that's all. In 3 dimensions, because of Schotten identities that relate, so antisymmetrizing 4 indices gives some identities for the variables that we were using to describe the vertex. And in particular for bosonic case, these are the identities one gets, starting from 2 derivative identities, then there are 3 derivative, 4 derivative identities. And taking these identities into account, even though we are solving the same equation as for general dimensions, but the space of functions changes in a sense because the variables are not independent, and the solution space completely changes in this case. So then we get very different solutions, even though we could expect this because we know that there are higher spin theories given in terms of Chern-Simons actions. But anyway, the Fronsdal program has its advantage, and in doing the analysis in the Fronsdal program naively gives some surprising results, but also kind of connects to all the other known things. In particular, we knew that there should be minimal coupling to gravity, and we explicitly get this kind of interactions. So when we involve either scalar or Maxwell fields, which have propagating degrees of freedom in 3D, we get that there are also some higher derivative vertices, but otherwise we will see that the number of derivatives is limited for general higher spin interactions that do not involve matter field. And maybe interesting observation is that if we are restricting ourselves to 2 derivative actions, so Fronsdal fields, then the only example which is specific in the sense that there are more than 1 vertices for a given collection of spins is the case when we have 3 Maxwell fields that interact between each other, and it gives either the Yang-Mills vertex or the F-cube vertex, which are both non-trivial in 3D. Why mention Maxwell? Because spin 1 could also be Chern-Simons in 3D, and this case is more similar to higher spins, and there we get only unique interactions for the Chern-Simons type fields. So Maxwell is somewhat unnatural. It's more like a matter field in 3 dimensions as opposed to Chern-Simons spin. Now, if we try to construct the gravitational coupling, so in 3 dimensions, Aragon-Tezev problem is not relevant because there is gravitational minimal coupling, and it can be written in this way. So we can also notice that writing this way, this is a very generic. S can be any integer number. In particular, it can be also 0, coupling to scalar fields, because this, even though there's s minus 1 here, but if we put s equal to 0, there will be another z3, so it cancels it. So we get y3 squared, which is the standard coupling to gravity. So this describes minimal coupling to gravity for arbitrary spins. And here, basically, we can see that the minimal coupling works because it is somewhat similar to higher dimensions, where we have spin-3 half fields, and when we couple them to gravity, this coupling is consistent only if the metric also transforms under the symmetries of the spin-3 half field. In the same way here, this coupling is consistent only if it induces transformation of the metric under higher spin symmetries. And therefore, it somehow enlarges the algebra of symmetries in the same way as in supergravity, spin-3 half fields lead to enlarging Poincare or whatever symmetry algebra is to supersymmetric version. So for general triplets that are all spin 2 or higher, then we have cubic vertices are classified in the following way. So we have no vertices if the spins do not satisfy triangle inequalities, and when they do satisfy, then we have 2 possibilities. When the sum is even, we have 2 derivative interactions. When the sum is odd, we have 3 derivative interactions. And when we want to do the parity odd analog of classification, we get the opposite result. Again, the triangle inequalities have to be satisfied, but there are now reversed that parity odd vertices with 2 derivatives have appear for the spin sums that is odd, and for even sum we get 3 derivative interactions. An interesting observation here is that, so I'm sorry for flashing so quickly. So U is the contraction of 3 fields with the epsilon tensor, and W is some contraction that contains 2 derivatives. So the interesting observation is that if we square U, then we get just, I mean, one can compute this expression because the square of epsilon is parity even structure, so we can get what it means. And an interesting observation is that one can explain this as a possibility of replacing U with Z's in some fractional powers, which in a sense makes little sense, but it turns out that by this interpretation, we are able to do some transformations on these vertices that a priori don't know about each other, the parity odd ones and parity even ones. And by shifting n's by halves, we somehow get the parity even vertices for free if we know the parity odd ones, and vice versa. And this is equivalent to a shift of s spins by 1, each of the spin. And it's an interesting analyticity in spin, which I mentioned because it led to some false conclusions that I thought that this would help also in deriving the fermionic vertices, in the sense that if there is some analyticity in spin, it can go beyond integer spin and maybe even beyond half integer spin. But at least there should be some way to see how to get the fermionic vertices. But also the naive idea would be that this z in the fractional power means that we have half of the bosonic indices constructed, which can be naively understood as like fermionic indices constructed. Each bosonic index can be translated via Clifford algebra to two fermionic indices, and so half would be naturally contraction of the fermionic indices, which somehow led to some ideas on how to do the fermionic vertices, which came out to be incorrect at the end, which I will talk about towards the end. So then one can also introduce interactions with Chern-Simons fields, which is kind of very natural. And also one can put the higher spin theories on arbitrary Einstein backgrounds, because when constructing this way the interactions, the Einstein equations get only quadratic in higher spin fields corrections. And if you have some Einstein background, it can be still solution for like all the higher spins being zero. Therefore, it's a good background to also construct the interactions. And then basically the coupling to gravity for higher spins is just covariantizing derivatives. So in this sense, this is a remarkably simple case where the problems of higher dimensions are not present. So the CFT dual of any higher spin theory would probably have 3-point functions that should match with the vertices that we derived, and this is something that was checked in work with Stefan Friedenhagen and Olaf Krüger. The part of those spins that satisfy triangle inequality is kind of obvious, because we know that Fronsdal fields correspond to two currents on the boundary, and which are chiral and antichiral in a sense. So therefore, each of them have their own operator product algebra, and so we know that there's two vertices for each set of spins, parity even and parity odd, in the same way that there are two independent structures of 3-point functions, chiral and antichiral, and so the number matches. But when there is the spins that do not satisfy triangle inequalities, it's not clear, because naively from CFT also there is such correlation functions, but this is somehow an artifact of possible filter definitions in the CFT, because in CFT the conserved currents are basically, as I said, chiral and antichiral holomorphic functions, and there is a freedom of redefining them, and this freedom can be used to define explicitly the basis in which whenever the spins of the currents do not satisfy triangle inequalities, their correlators are zero. This can always be done. This is a generic statement, and we've shown otherwise. For each chiral and for each antichiral, we have a unique standard 3-point functions, and this matches our classification. Now, if we can go beyond, we do arbitrary higher orders, and then that basically leads to a conclusion that also with the same properties, but now in higher point functions, we have polygon inequalities that are satisfied, which are iteratively derived from the lowest order ones, so not too much surprising. The important thing is that in order to match it from the bulk side, one has to make sure that there are no independent higher order vertices that violate this condition, polygon inequalities. But what we learned is that actually there are no independent higher order higher spin vertices at all in 3 dimensions. And then this, yeah, okay, I will go to already tell you the last part about fermionic vertices, and mention related stuff. So for the fermions, we can do similar program of constructing arbitrary general interactions, and this we actually have done in the recent work. And for higher order, independent higher order vertices, not cubic but higher order, which for the bosonic case we have already knew that they are all trivial in 3 dimensions. And for higher order, this was actually a master thesis of Philipp Lausch, who is a student of Stefan Fredenhagen in Vienna. And it was possible to show that generically all higher order vertices are trivial. It required a lot of technical work, but after all, there was not much surprise. What is more interesting is to study the cubic interactions with fermions. And here we notice that there is the only new part of this, in a sense, is the vertex generating operators that I described before. Now we also need to take into account there could be gamma matrices, and we have to introduce them in the vertex. But again, this naively will not change much the structure, and my expectation was that just by analytic continuation of the bosonic vertices, we may guess what are the fermionic ones. At the same time, this analytic continuation does not change the number of derivatives. So my guess was that there will be analytic continuation that only touches 2 derivative vertices with the fermions, but the 3 derivative ones will come out trivial for the fermions, and the 1 derivative ones would be appearing because of that we know that, for example, minimal coupling to gravity for fermions will be 1 derivative. But in order to actually systematically study this problem, one has to understand what is now the same equation that before should be solved in a different class of functions again, because the fermions come with their own identities. And of course, one has to derive all the Schotten identities and so on. But actually, all of these Schotten identities and so on are already encoded in much simpler identities, which are stemming from the just gamma matrix algebra and the condition that we are working with traceless transverse fields. So in this case, gamma traceless. And so we can easily derive just in the playing a bit with the gamma matrices, which I will spare time. I will not show you too much technical detail. So basically, one can derive such identities. And most importantly, it's basically that arbitrary antisymmetrized derivative of fermionic fields is R0 on shell, or at least proportional to traces of the divergences. And I think my headphones stopped working, but I hope I can still continue. If you cannot hear me, please let me. So what comes out is that identities are very strong in this case, and these are the identities that we get. And this basically fix all the interactions that can be between 3 fields, that the 2 are fermions and 1 is boson, turn out to be written in terms of 1 derivative structure. So only Y here contains derivatives. And so there are parity even ones, parity odd ones, but if we explicitly look at the spins, the parity even ones are those for which the sum of the spins is odd, I think, and the parity odd ones are when the sum of the spins is even. So for each given set of spins, there is only 1 vertex. So the natural expectation for me was that since in the bosonic case we had 2 vertices for each set of spins, there could be similar logic working for the fermions, but okay, it doesn't. And also, there is actually no way to have any analytic continuations between bosons and fermions because the number of derivatives does not coincide in these vertices. So the fermionic vertices have the property that they are all 1 derivative. So for each triplet of spins, we have only 1 vertex, and for spins that satisfy triangle inequalities, otherwise we don't have any. So this part is similar to bosonic case, and the parity of the vertex depends on the sum of the spins, and analyticity in spin does not mix bosons and fermions. And now one needs to understand how to interpret holographically, because the naive guess was that, so as the Fronsdal field is dual to 1 holomorphic and 1 anti-holomorphic current on the boundary, then for holomorphic currents, we know that there are unique 3-point functions for each triplet that satisfies triangle inequality and so on. So what happens here? Because we get only one vertex. So as a side remark, we have also again higher derivative vertices because if we include matter fields, then the possible vertices expand. I mean, in the sense that there are possible higher derivative structures that are non-trivial. So what we found generically confirms a more general statement that comes from our work with Maxim and Genia, where there we were basically dealing with bosons, but generically this also confirms that also for fermions this is true. That first of all, there are no higher order interactions. So this was one of the first kind of clues that give an insight that probably everything is Chern-Simons in 3 dimensions because there are no higher order deformations, only cubic. And in the first order form, the only cubic deformations are basically given in terms of Chern-Simons structures. So this statement is correct also for fermions. And so basically, if we don't have any propagating degrees of freedom, all the higher spin theories are basically Chern-Simons theories in 3 dimensions. Now, how to interpret the Fang-Fronsdal vertices, that there are only one vertex. So naively, again, we expected that there are 2 CFT correlators on the boundary corresponding to vertices, but we get only one vertex. But actually, this somehow can be explained by the fact that Fang-Fronsdal field has boundary degrees of freedom that are of a certain chirality. They don't come to different chiralities, even though the bulk theory is parity preserving. The boundary degrees of freedom are chiral. This is something that surprised me in some sense. So yeah, then this somehow restores the. I mean, there is no conflict with holography in the sense that now if we just deal with Majorana Fang-Fronsdal fields in 3D, then there's only one chiral degree of freedom on the boundary, and then we have only one vertex, which is either only chiral or only anti-chiral, or corresponds to only anti-chiral or anti-chiral correlation functions on the boundary. So we don't have pot. And when we take the Dirac Fang-Fronsdal field, it still doesn't come with 2 different chiralities, but both degrees of freedom on the boundary are of the same chirality. And so this somehow explains what this means also generically for holography. It basically is related to the fact that the fermionic boundary modes actually are not usually behaving same way as the bosonic ones, and this is more general than 3D. This has been noticed. I mean, some aspects of this were noticed in the papers that I could find. So already in 98, 99 by Artyomov, Frolov, and Markeno. And more recently, there was a related discussion in the paper by Campellion and Leonard. Yeah, I will stop here. Thank you.
Thank you. Are there any questions? Can you comment, so I'm not an expert on like 3D, how holography works there in comparison to general D? So you cannot just plug bulk to boundary propagators in vertices because there are no propagating degrees of freedom, right, in this case? So what do you do to get correlators?
Yeah, I never tried that, but what one can think of is that so the boundary dual currents in CFT can be somehow in one-to-one correspondence with the boundary degrees of freedom of the fields, because normally there's one-to-one correspondence with the bulk fields, but since the bulk propagation is somewhat empty, it seems that what is more natural is to think of the physical fields as the boundary degrees of freedom. Maybe I'm a bit, yeah, maybe I'm not fully consistent in what I say, because this is generic. It's more generic. The boundary degrees of freedom come with the dual fields. But how to compute the something like Witten diagrams? I never thought about it. So,
even at the very basic level. So if you think of representation theory, then well, representations that correspond to higher spin fields in the bulk, massless ones just do not exist, right? So what then are the correlators, the operators that correspond to these fields on the boundary?
that's
Well, I think it's something standard.
I think it's indeed about boundary degrees of freedom. So in Chern-Simons, you don't have bulk degrees of freedom. So all dynamics somehow happens on the boundary thanks to boundary conditions. And that's where you get two-dimensional CFT. So it's slightly different from what we have in higher dimensions, where your boundary fields are, roughly speaking, boundary values form kind of same representation as so there is a one-to-one between solutions in the bulk and configurations on the boundary. In thanks to boundary conditions, it's not the case in 3D, so it's different.
Yeah, my intuition might be completely wrong, but my feeling is that the topological theories in 3D, like higher spins without matter, the ADS CFT theory is somewhat trivial in a sense that the actual physical theory lives on the boundary, and it is dual to boundary CFT in some sense. So it's not real holography, but maybe I'm confused in some way. Yeah, one more thing I could add at the representation point of view. So ADS picture is quite clear in the sense that we have representation of massless higher spins is representations of SL2 plus SL2, which is the ADS algebra, and the fact that we have no bulk degrees of freedom is represented in the fact that the massless fields are those for which one of these SL2 representations are trivial. And this basically makes the representation to be much smaller in compared to generic representation, which would be the massive one where both are non-trivial. So good kind of criteria is the GK dimension of the representation, which for SL2 representations that are unitary is GK dimension 1. So, and if we have both non-trivial unitary representations, we will have GK dimension 2 that will sum up, and that would be a non-trivial field propagating in 3 dimensions. So particles in d dimensions have GK dimension d minus 1. So when we take the trivial representation of one of them, then for these massless fields in 3D, then basically we are effectively describing particle content in one lower dimensions. So this is somewhat related to representation theory can be understood in this way. But in fact, when we take the partially massless fields, then this is not the trivial representation of one of them, but the finite dimensional representation. And in this case, so there will be, so all of my discussion of this correlators and match and so on. So it is based on the fact that we basically have for massless fields, we have basically clear separation of the degrees of freedom into two algebras. But for when we introduce partially massless fields, this separation will not work anymore. There will be some mixture. Some fields will start to interact with both of the sides. I don't know in that case how to interpret the boundary safety.
Okay, I see. So you say it's going to be GK equal 1, yeah, which corresponds to, let's say, on-shell field in two-dimensional space.
Yes. Yeah.
Mm-hmm. Okay. Any other questions?
Pero, in 3D there is a one-parameter higher-spin algebra, and I wonder if you can trace it back using the neutral-like approach. Do you find this parameter?
Yeah, that's the goal of this work I mentioned that we are doing with somewhere I mentioned it with Stefan Friedenhagen and Philip Neckham. So this is, I mean, CZ-Posian work because we basically have to do a lot of technical work to derive what is already known, but in a different language. So we need to do the deriving basically just lambda Chern-Simons in the language of Fronsdal fields. And this is, I mean, already for just the SL3, spin 2 plus spin 3 is quite heavy.
That must be hard, yeah. Mm-hmm.
Yeah, but it's not impossible. So it's something that we are trying, yeah.
Okay.
Any more questions?
I mean, I can maybe continue commenting on that, is that the ideal thing would be that if one has a aegis lambda theory, even without matter already in the metric formulation, then adding matter to it should be a realistic goal, right? Once you have the theory in the metric formulation. And then, I mean, there are already some natural expectations that in order to be able to add the matter, it has to have a specific mass that is related to lambda and so on, which can be an interesting game to play, but we are still quite far from having this.
Indeed, there could be some ideals that you can recognize and factorize with. Mm-hmm.
Do you expect that it's going to be local?
Yeah, that's a very good question. I mean, if it was, then it would be the example of a theory that I was mentioning with 5 properties. But it sounds too good to be true, but so far there is no reason why not. I mean, there's no no-go theorem that clearly states that this cannot exist. Because the no-go theorems that work in higher dimensions, somehow already all the properties that for example, minimal coupling to gravity or the S-matrix arguments where we have higher spins propagating and so on. These are not present here. So in a sense, on one hand, it sounds as if it's very similar to the problem of higher dimensional higher spins. On the other hand, it might be somehow an example where you can avoid the no-go theorems. So, I mean, this is the motivation, even though, I mean, we cannot exclude that eventually we will get some, we will get stuck by some reason that we don't know yet.
I might add to this that from, let's say, from Vasilyev's point of view, the three-dimensional theory is very, it looks similar to chiral sector of four-dimensional one, which is local.
Oh, I see.
And I would not be very much surprised that the three-dimensional case would be local. The only problem from Prokrushkin-Vasilyev's point of view is that there is the coupling through topological sector that you have to get rid of. And while you don't do it, it is local, and non-locality may appear after redefinition of fields so as to get rid of the topological sector. That's just a comment.
Yeah, maybe that's I mean, one can get good hints from this so that one tries to do it properly in this setup. But when you say topological fields, I mean, I vaguely remember now. Maybe you can comment a bit more. So, I mean, already the higher spins are topological, but there is this sector that is somewhat twisted compared to standard.
Yeah, just unlike a name, some twisted sector, right? Mm-hmm.
I was also wondering on the concerning the comparison with the light cone approach.
Mm-hmm.
I think if you would ask Mitsaev, he would say that well, there is nothing to do in 3D because well, if you light cone gauge fix, then nothing propagates, so there is nothing to study. So like I'm like wondering, so these well interactions are non-trivial, right? In a way, with Chern-Simons, it does deform the theory.
Mm-hmm.
Which means that, well, essentially light conformalism does miss some kind of subtle interactions, but still some additional possibilities.
Yeah, I mean, the topological fields are still not completely, I mean, they describe something that is living on the boundary. It's not that they are completely empty systems. But yeah, the light cone might not see this. Of course, one can argue that maybe the right way to try to describe such theories, I mean, if you don't have motors, then maybe it's one can directly look at the boundary theory because the degrees of freedom are on the boundary and so on. But I mean, it depends on the person you ask. I think if you ask Massimo Porati, he will not happy with this kind of argument because he thinks that even though there are no propagating degrees of freedom on the bulk, there's a very non-trivial physics going on there. Like, I mean, we know that there are black holes and stuff, and also there's topological aspects that are interesting by themselves. So even if we don't have any matter, but when we add matter, then yeah, I mean the light cone would see only this only scalar fields, for example. I don't know what one can do with that. But yeah, the full off-shell theory might be still interesting because it has infinite symmetries.
Okay. So any more questions? Okay, it seems that we don't have any other questions. So thank you very much.